Hello everyone. In this Jupyter Notebook walkthrough, I wanted to show you how you can align two point clouds, one collected with an airborne lidar dataset and the other with a UAV or drone dataset, and how you can align them to each other using Open3D and some additional information that will allow you to evaluate these things. So we are going to walk through the Jupyter Notebook ICP registration ALS UAV. And before we open up that notebook, we need to make sure that we have activated our environment, and then we call Jupyter Lab on that particular environment for the Jupyter Notebook file. And that is a longer notebook that we slowly walk through and making sure that you can read those fonts by increasing the font size somewhat. And this is a slow walkthrough to aligning a UAV to an airborne lidar point cloud. That's a fairly typical thing that you have to do when you collected an UAV data set and you would like to align it to an existing, likely much more precise airborne lidar data set. Importing some things here in the beginning, the standard matplotlib, numpy, Open3D, and lastpy functions. Defining some functions that you are already somewhat familiar with. Here is a function that allows us to draw two point clouds with a uniform color. Again, orange and cyan are the colors. Defining a function that allows us to draw two point clouds, but also provide a rotation or transformation matrix that is given in the 4x4 form in the transformation. And I'm defining the getColors function that we used before in the visualization tutorial. So the first thing that we are going to do is we are going to use our airborne lidar point cloud. That is a point cloud that is too large to be stored on GitHub. So this is a link. That link gets you to download the LAV point cloud, which is an airborne lidar data set from the campus GOM. Please put that in the directory where you're currently working in, or you need to provide a separate path. We are going to use lastpy read to open up that data set. And we are going to extract the XYZ coordinates from it. And then in the next part, we are going to turn this into a Open3D data set, because we also would like to visualize this and take advantage of some of the faster algorithms that have been implemented in Open3D. So we are bringing this into a point instance of Open3D, and then we are downsampling it also to 1 meter, because we are going to use with the 1 meter downsample data set just because this tutorial should go quick, and working with fewer points will allow us to work through it fairly fast. And in that next instance, we are calculating normals. As I have explained before, these are useful for visualization and many other things, specifically when we talk about alignment, and I'm pointing this out later in this tutorial. And last but not least, we are orienting our normals all upwards in the positive Z direction, because we know that for an airborne lidar data set, things usually point upwards. So loading these data will take a second, because we are dealing with 13 million points that first need to be read by the LAV file, and then needs to be converted into an Open3D format that allows us a fast visualization. So we have just loaded the 13 million points and also downsampled them to 640,000 points for faster visualization and working with the data. So let's look at the data set by drawing the geometries. This is the point cloud here. You see construction going on the campus GOM in the University of Potsdam, but you also see that there are a couple of outliers or other reflections above and below that point cloud. So up here we have reflections that are associated with birds that have been active during the spring and summertime in this region. So this is definitely something that we probably would want to filter out. And then we also below the point cloud have typical reflections that are associated with windows or with other lakes that we have on campus that essentially extend the pathway of the LiDAR beam, but are not the original distance that the LiDAR beam has traveled. So this was a quick visualization of the downsampled data set, and I just wanted to show you the differences between these two data sets. This is the visualization of the original and the 1 meter data set. One is the downsampled version, and one is the original version. It's a little hard to see the differences. You may want to press minus. That decreases point sizes, and here you can see now that the orange point cloud is a fairly dense LiDAR point cloud. You see the orientation of the LiDAR beams, but you also see the blue points in between here. These are the downsampled voxels in a more or less regular spacing. So we are going to continue to work with a 1 meter data set, but mostly to make this computation go much faster. When you work with full resolution data, you are likely to receive similar results, but it will take a little longer. I also wanted to point out that once you start working with larger point clouds, you may want to clean up your memory off and on. That's the same with Cloud Compare or other computers. Here I am on a Linux Ubuntu system, and I'm going to look at how much memory I have left. There are similar things that you can do on a Mac or on a Windows. Currently I have 65 megabytes total, and I have 65 gigabytes total. I have roughly 15 gigabytes left, and I am going to remove a couple of points or a couple of number arrays to save up some memory. For this particular desktop that I'm working on, I don't need to worry about the memory because I have 64 gigabytes available. But if you have a smaller environment with maybe only 8 or 16 gigabytes, you want to make sure that you have sufficient memory available. So I'm just deleting them by setting them to none. That removes them from the memory. And if I'm now calling my memory info again, I see that I have a total of 16 gigabytes available. I essentially removed 1 or 2 gigabytes from that environment. Again, for that specific system here, it's not crucial, but if you work on a smaller laptop, this will come in handy if you're working with multiple point clouds. The second point cloud that we're loading is a UAV point cloud. We call this PC2, or then the Open3D dataset PCD2. Again, this point cloud is large. Please download it from the Dropbox link here. You can bring it in through LastPy. This is a file name. It's it was collected with a solar camera on board of an EB for the same area. We are going to do we are going to do the similar steps as we have done above by importing the data. The only difference, or the only addition that we do, is we are also bringing in colors. Because the UAV data contain color information, we can bring in the red, green, and blue attributes, and we can stack them into a color matrix, and we can pass that color matrix to Open3D. We need to make sure that the colors are between 0 and 1, and the RGB values that we read out are usually 8-bit, or in that instance, these are 16 bits, so we need to divide by 2 to the power of 16 to make sure that our values are between 0 and 1, and then we end up getting realistic colors for that particular data set. This is a fairly large data set, and it takes a while to load it. We are talking about 24 million points that we are then also downsampling to 1 meter voxels, and in the end we have roughly 480,000 points. So let's look at our downsampled point cloud. This is a typical UAV data set. You see the colors, the nice color set. You see it's downsampled to 1 meter. You see the coarser spacing here, so this is not the original spacing from the UAV data set. And you're also seeing many reflections and wrong alignments that occurred during the photo generation, and this is definitely something that we need to clean up. But it's pretty typical that any data set that has been collected from either airborne LiDAR or from UAVs need to be filtered and cleaned up. We can also look at both point clouds. Again, the downsampled and the original one that nicely shows us how I'm going to hit minus a couple of times to make those points a little smaller. You see the very, very, very dense point cloud in orange. That's the original UAV data set. And then you see the spacing, the more regular spacing of the voxel grids in cyan here. And I'm going to remove the original point cloud because that will help us to free up some memory. 24 million points is quite large to have continuously stored in the memory of your system. What I'm doing next, I'm showing both point clouds, the airborne LiDAR one and the UAV one, the subsample data set, just to get a first impression how well they are aligned or offset. And what we immediately see is that both point clouds are offset in the Z component, and that's fairly typical because one is in geoid coordinates and the other not. So that's fairly typical when you have an airborne LiDAR data set, that you have some UTM reference points that use a different geoid than the WGS84 being used by the drone data set. So we clearly see that there is an offset in the Z direction, but there's also certainly some offset in the XY direction. So this is something that we would like to align these two data sets against each other and make sure that we do this automatically. Before we do so, I would like to point out again the large amount of noise that is in these data sets. And this is something that we definitely would like to remove before we proceed, because when we align two point clouds, they should be noise-free, then the alignment is much more reliable. We call that step outlier filtering. There are different approaches that exist. Here we are going to use a simple statistical outlier removal that is also implemented in Open3D. It essentially takes a neighborhood of points, k equals 12 or k equals 24 neighbors, and it's going to use a threshold of standard deviation that everything above that threshold is being removed from your point cloud. So the first step of this is that you're generating the average distance between points for the entire data set, and then all the points that are above a certain standard deviation of those distances are being removed. And we are going to explore this a little. That's a typical step that you end up doing to clean up your data. And before we do this, we are defining ourselves a little function that allows us to visualize the results. This is just the inlier and outlier cloud that we are generating. Again, showing them in two different colors, one in gray, one in red. And this is just a way to see what is that filtering step doing to our point cloud, because very often you need to experiment with this a little to find the ideal parameters, and you often have to do this repeatedly. So that's a nice thing to visualize the points that you're filtering or the points that you're removing, because it is as it is. You're often also removing points that you would like to keep, and you need to find a nice middle ground between this. So we are going to call the remove statistical outlier filter on our original 1 meter voxelized point cloud. We're using a neighbors of k equals 6, and we are saying everything that is further away than 2 standard deviations of all the points should be removed. And in the last step, we are also visualizing this. This is the first cut that we are doing. So in gray, we see all the points that we keep. In red, we see the points that have been identified as outliers. So good thing is we have identified a couple of points here up in the high sky. These are the birds' reflections. Those would be removed. We also see that a couple of reflections from large windows in lakes would be removed below ground. That's a good thing. Not all of them, so not all of them will be removed, but we can call it a second time. What we also see here is that we are also going to remove some points that we would like to keep, for example, on a facade or some points of trees. And that is just the fact that those points are very, very, they are removed from other points, and thereby they are being identified as noise points. So we are going to call this again now with a slightly larger neighborhood. And so we are going to remove those red points, even so there are some points in there that we would like to keep. We are going to remove those red points by selecting only the points that are the good points. And then we are going to call this again on the resulting point cloud. And now we are seeing that we are going to remove some additional points, and we are going to definitely remove the additional points below ground. So we are filtering out the below ground points that exist here, but we are also removing valuable points from the facades. There are other ways to optimize this, but let's just go with it for now, because we want to align the point clouds and not necessarily have the full resolution point cloud available. So we are doing it one more time, and we are making sure that we are really removing all the points below the ground, and this now here is being selected, that little cluster here, which should make us happy. So we did 3 iterations. The third iteration looks like it's most useful. We are bringing this back into our original 1 meter point cloud, and we are removing the other point clouds. So we are throwing away the point cloud that contains noise, and we are going to use the point clouds that we have filtered. I also want to point out that there are different ways of doing this. You could have classified your point cloud first and then remove points below the ground, or you could have manually selected this. Again, there are different ways to reach the goal. The goal is that you end up having a point cloud with a minimum number of outliers. And this is what we end up getting. If you look at it from the side, you don't see any significant numbers of point clouds below the surface again. And I also don't see any high point clouds, high points up in the air. And the color scale also looks reasonable because we have now outliers in there. So this is a cleaned up data set that we can now use for alignment. We need to do this also for the UAV data set. So we approach it in the same way by calculating our inliers and outliers, and you immediately see that there is much more noise available. And we first the strategy here is to first remove points that are fairly or small clusters of points. You see this large cluster here of points where we have to use a different strategy. I'll explain this in a second, but for now we are going to remove points that are fairly isolated. And that looks like that we can do that with a fairly small numbers of neighbors. We are going to repeat this step by calculating the average distance of 8 neighbors and using a cutoff threshold of 1.5. And it looks like as if we are going to remove a few more points from the ground. We are going to do this now with a much larger neighborhood. And the idea here is that we are going to identify that problem area that is fairly large below that surface here. So I'm talking about this area and this area. These are larger clusters. But it looks like that if we identify the mean distance for a larger number of neighbors, we are getting at identifying and selecting those, at least some of those points. We are also removing some useful information, such as some trees, because they form similar clusters, but we don't want to use the trees for ICP alignment anyway, so this is not something we need to worry about it. We are going to call this again just to make sure that we also remove the last remaining parts here. And now you see that those have been selected. This guy here is all in red, which is a good sign. And it looks like as if we have removed a lot of noise that is below that surface with a few quick steps. So we did 4 manual steps here, and we are going to use the 4th iteration and put it back into our original point cloud, and we do some last visualization that allows us to look at the entire point cloud again, and it looks fairly reasonable. I don't see any outliers below, I don't see any outliers above, and I think we can use that point cloud for our alignment step. Before we do the alignment, we probably would want to look at the initial offset of the point clouds, and this is here where we are going to use metrics that we have introduced earlier. We are looking at the distribution of the point clouds. So we are measuring the initial offset of point clouds using our CKD tree. Here, as a reminder, we can access our point coordinates with NumPy as array, and I'm pointing this out because we are working on the 1 meter downsample data set where we don't have the original NumPy array, but this is a way how you would access this. We use our CKD tree, and we are calling the distances from A to B and from B to A, always the closest distance, and we are using as many cores as we have available because now we are working with 500,000 points. It takes a few seconds, but really only a few seconds. It's still a very, very efficient way of looking and sorting through your data set. And now let's visualize our distance. And our distance from point 1, from the airborne lidar distance to the UAV lidar to the UAV distance is shown in blue. So these are the distances now in meters, the distribution. So it's roughly an average of 30 somewhere. And the distance from point 2 to point 1 is shown here. That is that spike here where we also have those images we're taking it, or the point clouds are from different times. They're not exactly from the same timing, so the objects are different, and we had the one construction site on one of the images with a high crane that is providing that large offset here. I pointed out before that we can visualize those distances spatially, and so we are subtracting the mean UTM coordinate, and we are showing the distances for both point clouds from the first distance from A to B and the second from B to A. We're only showing every 10 points because otherwise this would be too dense. And this is a way of visualizing those points in a spatial sense. So the distribution that we just looked at, those blue and orange curves, this is shown here as a map view. So we clearly see where we have the areas with higher distances and lower distances. This is just for your visualization purposes to get a better spatial understanding of what that distribution would look like. These are not UTM coordinates here anymore. This is mean subtracted distance. That's just to make those numbers here more readable, but these are still meter distances in the XY grid, but also the color is a metric scale. Okay. Hausdorff distance. This is the maximum distance, the worst case scenario. We looked at that in the previous tutorial. Our worst case scenario, our maximum distance is 54 meters. Maybe not very useful, although when you have a cleaned up data set, that clearly tells us it's a large offset between it. We are going to use a modified Hausdorff distance because I think that is, in this instance, more reasonable. And the modified Hausdorff distance is the maximum of the average distances, is roughly 30 meters. And if you look at our distribution again, you know, if you kind of look at it with some squeezed eyes and bend far another way, you could make yourself believe that 30 is the average distance for both of those distributions that we see here. Just for the completeness, we can also calculate the minimum distance of two sets of points, the best case scenario. I'm not going to discuss this in detail. I'm just pointing out that we can get the minimum distances, and that these distances that we just calculated can also be calculated on the command line. So we can call Pidal Hausdorff on the source and in the candidate data set, and you can also call it for the chamfer distance. I'm pointing out that this is taking a little longer, and that if you call this on this data set, then it's not a cleaned up data set, but that would be something that you could do on a command line if you feel uncomfortable with the setting here provided by the Jupyter notebook. It's much slower because the PDAL implementation only uses a single core, whereas the Open3D and SciPy CKD tree approach is a multi-core approach. Okay, let's move on and continue to align those 2 point clouds. The initial offset of those 2 point clouds, roughly 30 meters, right? Let's use our modified Hausdorff distance, indicates that we cannot do a fine alignment right away. We need to do some global alignment first, bring them into the same reference frame before we can do a fine-scaled ICP alignment. There are different approaches. You could do this through manual clicking. That's relatively easy to do in Cloud Compare, but you can also use more sophisticated approaches that automatize some of those steps for you. And the idea here is that you are using more information about the neighborhood of the points, and you're calculating a feature point histogram for each of the points. So you're looking at the neighborhood of the point, for example, at curvature and at other additional parameters that allow you to better identify the neighborhood of each of the points, and that allow you to generate better matches. So the implementation that we're using is feature matching. And we are going to use this, but we are also going to even further downsample our point cloud, because for that initial global alignment, we can use a fairly coarse point cloud. So that 30-meter offset can also be determined in a 5-meter data set. You don't need to use a 1-meter data set for this. So we are going to define a source and a target point cloud, and we are just down sampling it to 5 meters. And so our source is our UAV data set, and our target, the reference, is our LiDAR data set. So we have source and target, and we are going to calculate our feature space. That usually takes a second or so, and I'm going to talk about this in a second some more. So we are going to calculate the feature space for all of the points. We now have a new variable which is called source 5-meter feature histogram, fast feature histogram, and the same one for the target point cloud. And that is a 33-dimensional vector. So each of the points now has 33 attributes, and those attributes describe the feature histogram. I put a few additional information in here. This is something that we are going to discuss in more detail at some other point. I'm just pointing out here that a very common way of identifying and matching points is to make sure that you're matching the right points. And you do this by calculating a point feature histogram. And the point feature histogram, for example, looks at the neighborhood of each point and looks at the things such as curvature, second order moment invariance in all different directions. So the curvature in the XYZ, the different invariance in the XYZ direction. So you pretty quickly come to 33 parameters that describe the neighborhood of your point. So it's a spatial descriptor that allows you to link points that are more similar to each other. You can visualize these points or these parameters if you would like to. This is shown here. I'm just showing the first 4 parameters without going in any detail here. I'm just pointing out that now each point of your 5-meter data set has 33 dimensions, and each of those dimensions contains information about the neighborhood in the XYZ direction. And those are being used for matching similar points. And I'm just showing the first, second, and third feature here. This would be essentially in 3 different directions. And I just want to point out that there is a spatial pattern to it that can be exploited so that you make sure that you're only aligning points that are similar to each other. Again, this is something that we are going to discuss in much more detail in the in-person classes. So we can use that feature histogram and perform a global registration. Which means we have our source point cloud, our target point cloud, we have the source features, the target features, and we are only going to merge the points, or we are only going to align the points that have a similar feature space. And we also give the maximum distance that the points can move. This is the distance threshold here. So this is something that is done pretty fast, and the result of that procedure is the transformation matrix. So we have our 4x4 transformation matrix with the rotational components here in the first 3x3 parameters, and then the translational components here in the fourth column. We can verify our result by sending the source and the target information and also the transformation information into our viewer. So we are looking at both of the points. The first thing that we notice is that they are now perfectly aligned along the z-axis, or pretty well aligned along the z-axis. You see that maybe the points in the XYZ direction are not perfectly aligned yet, but it looks pretty good. I mean, as a first order assignment, this is pretty good. I mean, if you look at it from this side and if you rotate it a little, you see that the walls are still misaligned. But that's okay. I think that's a good result that would allow us to do now a much more detailed ICP fine-scaled alignment. I just wanted to point out that there is another way of performing this by using a random sample consensus. So you iteratively approach a result that then is giving you the best alignment between this, and you do this repeatedly until you get the best alignment. I'm not going into detail here in this walkthrough. This is something that we are doing in the in-person discussion. I'm just pointing out that this is a different approach that gives us similar results, and in some cases even better results. We are still using the feature matching, but we are doing this operation several times. So I'm going to use that ransack result estimation for now, but in the end, for this particular example, it would be very, very similar. So you could, if you say that now, if you're happy with this global registration, you can also apply that transformation, and then you have a new registered point cloud, UAV point cloud, that you could also save to a new file if you want to. So this can be obtained by creating a deep copy of your UAV point cloud, so you're not overriding the memory with this, and then you are assigning the transformation to this that would allow you to rotate and translate the point cloud based on those transformation and rotation matrices. Okay, let's do a quick assessment how well we have done by doing the global matching. And we are going to look at our Hausdorff and modified Hausdorff distances again. And our initial Hausdorff distance was roughly 54 meters, and now we are down to 43 meters. Again, let me point out that this is a worst case scenario and maybe not the most useful one here. The modified Hausdorff distance is more useful. The average distance after the global alignment is 2.3 meters. That's pretty good. So we went from 30 meters to 2.3 meters. That's very nice, and we can also display this in a histogram sense. This is our original distance between the airborne lidar to the UAV, and then UAV to the airborne lidar with a 30-meter modified Hausdorff distance. And now we have shifted that histogram much closer to 0 because the points are much closer aligned. So we have a much better match between those two points. So I should point out, you can safely do this alignment that we have gone through here with a global alignment using the fast point feature histograms, because the resulting transformation matrix can also be applied to the full resolution point cloud. So you have that 4x4 transformation matrix that you can use to rotate your full resolution point cloud so that both of them align. That's just as an addition, so it's fine in this case if we work with a downsampled version. And in fact, what we are doing here in the fine alignment now, the next step is we are taking our 1 meter data set and we are applying the transformation that we have calculated from the 5 meter downsampled data set. So this is something that is a nice way to do, because it's often faster to work with a 5 meter alignment data set than a 1 meter data set. So we are doing a simple ICP registration. The details are being discussed in the classes. This is a simple point-to-point registration. So you're trying to match the closest point to each other. And this is fairly fast, given the parameters that we used, and what I'm just printing here is the transformation matrix. So usually the diagonal that would indicate the scaling is 1, and this is 9.999 times 10 to the minus 1. So this is almost 1, and then we have the translation and rotation components here in the first fields. So if we are going to look at this, we draw both point clouds, and it looks like as if those point clouds generally match pretty good. I think so, yeah. And it's a challenging alignment because the point clouds are different in the sense of that the lake is represented in the UAV point cloud, and the one point cloud also contains the crane and the construction site. So I think it's generally a good results. But there's always room for improvement. But anyway, this is something that we probably can go with. And then last but not least, if you're happy with this, you can apply this transformation, and you can also calculate the distributions of the aligned data set. So we are taking now our target in our aligned data set, and we are calculating our histogram for the last time, and we are seeing that our ICP modified Hausdorff distance has improved the original distance offset a little bit, but looking at the full distribution, you clearly see that it has improved by quite a bit. So let me walk you through here. So this is the original distribution of distances from the first step of the global alignment. We went from 30 meters down to roughly 2.5 meters or 2.3 meters. This is the distribution that we see here. On the right-hand side, the x-axis has changed from 0 to now 12 meters and not from 0 to 40 meters anymore. And we are only comparing the results from the global alignment versus the ICP alignment, and that darker color is the global alignment. You see that they are shifted further to the right, so they have a higher overall distance, and then the lighter reddish and bluish colors are the ICP alignment that have shifted more towards 0. Maybe you could tweak the parameters a little and improve that fit, but this is definitely something that is a fairly reasonable result at first order in the amount of time that we now have spent with this alignment. So I'm very happy to discuss this in more detail and also provide additional information of ICP alignment point to plane or color-based ICP alignment that then will end up providing better results, but are also usually somewhat more time sensitive. So we can discuss all of these things in person or in other channels.